All right, everyone. Welcome to the first intro video for Redox Reactions. That's chapter 9.1. If you're watching this, that means you've made it to the final, stretch of the course. Now you've been working hard and you've reached the end of organics. So congratulations, you've made it through. I hope the experience was good for you and you've learned a lot because sort of being proactive, looking up answers on your own, researching things on your own using different resources without too much of a guidance from your teacher and exploring things on your own and discovering things on your own. I think it's going to be a good foreshadowing and a good experience right before you head towards university. Get used to it. Don't feel afraid to step out and look up answers on your own. Um, that's sort of what real life is, you know? Anyways, without further ado, I'm going to continue on with redox reactions. The next couple of weeks as we finish off the entire year, I thought it was going to be useful for you to know what redox is before you head towards university. I don't want you to be any less prepared than other people that are entering university. Okay, so redox reactions, what are they? They are reactions that you already know, you've already seen, but we classify it a little differently because conventional means of just swapping ionic compounds, for example, for this single displacement reaction that I have right here, it's not enough to really explain where it's coming from. It's not enough to explain why there is the ability to conduct electricity, why this is able to produce potential energy, like, for example, a battery. There's all these different properties to this that's not explainable just from, you know, taking this and pairing it with something else, right? Or a single displacement. It's not the same. We have to go past the grade 10 level. So here it is. Do you remember in grade 11, you were given a reaction, whether it's a single displacement or double displacement of ionic compounds, and you were asked to write a net ionic equation. I'm going to do that with this one now. Copper is not ionic, it's just on its own. But silver nitrate can be written as 2 silver ions if it's an aqueous, because that dissociates, right? And 2 nitrate ions because they dissociate in water, aqueous. Aqueous. But after the reaction, we have 2 atoms of silver. We have 1 copper ion, 2 plus. So it would be cupric, okay? And 2 nitrate ions. Of the products and the reactants, 2 nitrate ions, they don't change. And so they are crossed out. They are spectator ions, leaving us copper and 2 ions of silver, turning into 2 atoms of silver and copper, 1 copper ion. And up to the grade 11 level, that would be correct. But now that we're talking about redox reaction, I would like to zone in, home in a little bit closer to this final reaction that you wrote me and cut it into 2 different parts. Let's focus on the copper. What happened to the copper? Copper used to be a solid, and then it became copper ion with a 2 plus as its ionic charge. How did it gain a 2 plus? Well, if you use your grade 9, 10, and 11 chemistry skills, I guess, you would say that it lost 2 electrons. So Cu2 plus and 2 electrons would equal copper atoms, right? 1 copper atom. In the same breath, I had 2 ions of silver with a charge of +1. But somehow, that charge of +1 disappeared and it became a solid. How? Well, it gained 2 electrons somewhere, 1 electron for each ion, and it became 2 silver atoms. This reaction here, so how about I just, I color this in blue, and I color this in red, these two half reactions, because these, the copper half reaction and a silver half reaction together create one full reaction. These half reactions are reduction and oxidation reactions. One of these two reactants was oxidized. One of these two reactants was reduced. How do we know which one is which? Well, here's how. Take a look at the ionic charge. Right now, the ionic charge of copper was a 0, technically, because it's neutral. But that charge became a 2+. From 0 to a +2, did the number increase or decrease? It increased. That is what we call an oxidation. In the same way, take a look at the ionic charge of silver here and the charge of silver here. It used to be a 1, and then it became a 0. Did the ionic charge increase or decrease in this particular case? Decreased, or it was reduced. So we call it a reduction. And henceforth, a reduction and an oxidation together creates a redox reaction. So with one example, I was able to cover half reactions. I simply talked about oxidation numbers, and that's simply what this is, and oxidizing agents and reducing agents. That's my last one. Which one of these two was oxidized? The copper was oxidized. Correct, right? Which means, what caused the oxidation? The silver. You get it? I'll say it one more time. For copper to be oxidized, it had to give away 2 electrons. For silver to be reduced, it had to gain 2 electrons. Correct? So for silver to be reduced, it needed copper to do something to it. Copper is the agent that reduced silver. And silver had to, so for copper to be oxidized, it needed someone to take the electrons. Silver did that. So in this case, silver would be the oxidizing agent. And that's it. Those are the 3 sort of ground laying, I guess, the foundations that are required to understand how to interpret redox reactions. And the example here is going to be very helpful in navigating some of the textbook questions that I'm going to assign. So just to make sure everyone understands how to identify the half reactions, and then how to identify the oxidation numbers, I am going to go through one question from each section here. Okay? I'm going to clear the screen, but if you might want to pause the video, I'd like you to write that down. Do as many of these as possible. I think it's going to be good practice before we get to chapter 9.2. All right? So starting with page 601, I'm going to clear the screen in 3, 2, 1. Page 601, number 1A. Write the oxidation and reduction half reaction equations for the following redox reactions. Bear with me here. But if you want to actually let this video roll while you bust out your own textbook and get out a piece of paper so that you can follow along, that'd be good. So this is a net ionic equation that the textbook is providing you. Which one was oxidized and which one was reduced? Well, let's start. Starting with tin, 2+, it became tin atoms, or a tin atom. For tin as an ion to be satisfied, I guess, to lower the oxidation number from, or the redox number, the oxidation number from 2+ to nothing, it must have needed 2 electrons. And this Because I know the number decreased, it was a reduction. Cobalt, on the other hand, became cobalt 2 plus. Well, if it became 2 plus, that means it must have lost 2 electrons somewhere. The oxidation number went from 0 to 2. It increased, and so we call this an oxidation. And of course, as a result, you would say tin is a oxidizing agent, just for practice, and cobalt will be the reducing agent. It caused the reduction. Okay. Okay. Try the other questions. I'm going to move on. This is going to be page 604, number 1. It goes through trying to identify what the oxidation numbers are. I'm going to go through as many of these questions as possible, but there are some rules that will help you, some foundational rules that will help you in identifying oxidation numbers, and that's in page 603. There's a chart, there's a table 1. So take a look at that. In short, typically this is all you really have to remember to not be confused. Number 1, all atoms, like for example, cobalt, right? All atoms on its own always has an oxidation number of 0. And I think that makes sense. Any elements on their own that are not ions have an oxidation number of 0. Okay? A monatomic ion is the same as its charge. Like for example, if I just have Na plus, if I have Cl minus, if I have Br minus, if I have Sn2 plus, well, I think it sort of makes sense. Whatever that ionic charge is going to be the oxidation number. One thing that you would want to remember, fluorine, no matter what, is going to be a -1. Okay, it's going to be a -1. And that sort of is funny. You would think that, hey, yeah, obviously fluorine is going to be -1, just like bromine, just like chlorine, just like iodine. Actually, that's not the case. Fluorine is the only one that will always be -1, and all the other ones we've mentioned so far, there might be some exceptions. Okay. Number 2, hydrogen is essentially almost always going to be +1. Take a look at what the chart says. Okay, and lastly, oxygen is almost always going to be -2, except for peroxides. But we'll get to that in just a second. Okay, here's some examples. If you take a look at, let's see. Let's see. Okay, so number 1, A. Nitrogen gas. Nitrogen gas on its own. Determine the oxidation number of nitrogen in each of the following substances. For nitrogen gas, the oxidation number would be just 0. Okay, there is no charge per se. They're equally shared. It's covalent. You don't have to worry too much. If you're a little bit confused, take a look at the first rule of table 1. An atom in an element is 0. Part B, NO2. Now it gets a little bit interesting. Okay, the oxidation number of nitrogen. Well, I'm not quite sure what it is, but I do know that according to the rules on table 1, the oxidation number of oxygen is -2. I'll keep writing 2 minus, -2. And how many oxygens are there? 2 of them. So in total, the oxygen portion of nitrogen dioxide would have a total, I guess, oxidation number, of -4. Okay? Which means nitrogen needs to balance that. How do I know this? There's a thing called a zero-sum rule, but more so than memorizing a rule, take a look at this molecule itself. Does this molecule, nitrogen dioxide, does it have a charge? No. That means the overall charge has to be a 0. And as I said, if the oxidation number of oxygen is -2, and I have 2 of them, in total the oxidation number will give me a -4. That means the nitrogen would have to be a +4. I know that's very different. This is not ionic charge. Okay, it serves very differently. These oxidation numbers are necessary, and it makes a lot more sense to see what charges are being changed, where the electrons are moving in a reaction, so on and so forth. And as the reaction gets more and more complex, redox reactions help, or oxidation numbers help to explain very, very complex reactions. So start learning this new system, okay? Let's try a couple others. Question C, N2O. Once again, in this particular molecule, the oxidation number of oxygen is still the same, it's -2, but I only have 1 oxygen, which means the rest of the nitrogen needs to balance out an overall oxidation number of -2. I have 2 of them. -2 divided by 2 nitrogens, that means each one is going to have an oxidation number of -1. Part D, NaNO3. Oof. Typically, alkali metals, okay, or monatomic ions, it's going to have a charge of +1. Okay, and we know before all else, oxygen is always going to have a oxidation number of -2. I have 6 of them. That is going to be -6. Sodium is a +1. That means nitrogen must be a +5 to balance out and cause the zero-sum rule to take effect. Okay, part E, NH3. So hydrogen is now popping in. If you take a look at table 1, it does say that hydrogen is always +1 in its covalent compounds. The only exception is metal hydrides, in which hydrogen is going to be a -1. I know that's really weird, okay? In this particular case, it is not a metal hydride, it is a covalent, which means hydrogen is going to have an an oxidation number of +1. Having 3 hydrogen means it's going to have a total of +3. That means nitrogen has to have an oxidation number of -3. I know. The oxidation number of nitrogen has been different for every single example, but that's the point. And you know what? When these react, those oxidation numbers will come in handy in explaining how the reaction occurs. Okay? Let's try some other examples. Okay, number 1 of page 606. I'm going to clear this in 3, 2, 1. Page 606, number 1A. Copper, solid, and 2 silver, or it's the exact same one as we did before, becomes 2 silver atoms and 1 copper ion. Identify the entities that are oxidized and reduced in the following reactions. I see that the oxidation number went from +1 to 0. That means the oxidation number went lower, it reduced. The oxidation number from 0 became +2, it increased. So I know that's going to be an oxidation. Shall we try a slightly different one? Part B. 4 atoms of iron plus 3 oxygen molecules became 2 Fe2O3 solid. All right. What is the oxidation number of iron? Well, it's just an atom. It's 0. It's an element. How about oxygen gas? Again, the element is 0. However, in this particular molecule, we know that oxygen is always going to be oxidation number of 2 minus. I have 3 of them, which means the oxygen portion of this molecule will provide -6. I have 2 irons. If I want all of the oxidation numbers to give a balance 0, that means iron alone must be +6. I have 2 irons, so I'm going to do the +6 divided by 2. The oxidation number of iron, each of them, is going to be +3. So let's talk. Oxygen went from 0 to -2. Did the oxidation number increase or decrease? It decreased, or it reduced to a lower number. So this is a reduction. Okay. And for iron, it went from 0 to a +3. It increased, so that's an oxidation. Okay. Get familiar with redox equations, half reactions, knowing what's the oxidation agent, reducing agent, what is being oxidized, what is being reduced, and you'll be very ready for 9.2. Just as a final sort of goodbye to the video, you will see a very interesting acronym being used to help you remember whether it's a reduction or an oxidation. I think it's easiest just to look at the numbers. If it went from 0 and it went lower than 0, well, it's reduced, it went lower. But textbooks tend to enjoy giving this. Leo the lion says grr. I didn't make this up, okay? But this stands for, Leo stands for losing electrons, oxidation, right? Gain electrons, reduction. That never helped me, but I have met many students who prefer this and do not like my number going up and down method, okay? So take a look. For number 1B, iron went from 0, but if it went to plus, that means it lost electrons. It lost electrons. So it must be oxidation. This oxygen molecule went from 0 to -2. Well, if it became a negative, it must have gained electrons. It is a reduction. Leo the lion says grr. Never worked for me, but it might work for you. So again, please try all the questions that I wrote up in the beginning of the video. Practice hard, and we'll see you in the next one.